Hello everyone, my name is Debodip Chowdhury and in this presentation I will introduce my end-to-end predictive maintenance and machine failure prediction project. The aim was to answer a practical industrial question: can we use routine operating measurements to identify a machine that is likely to fail before that failure causes unplanned downtime? I worked with 10,000 industrial records where only 3.39% represented machine failures. This made the project both useful and technically challenging because failure was a rare event. I developed the complete solution from data validation and exploratory analysis to feature engineering model comparison, explainability, and deployment in an interactive Streamlit application. Before discussing the project, I would like to introduce myself briefly. I am a data science and AI professional based in London with experience across data science and data analytics roles. I hold an MSc in financial technology with data science from the University of Bristol's uh, and my background is in computer science. I am also a Microsoft certified data scientist. My technical experience includes Python, SQL, Apache Spark, machine learning, analytics, and large scale data pipelines. This project reflects the kind of work I enjoy most: converting data into a complete, understandable, and deployable decision support system. My LinkedIn and GitHub profiles are shown here for anyone who'd like to explore more of my work. Now let us move to the business problem. Unexpected machine failure is costly because it can interrupt production, increase repair expenses, reduce equipment life, and create operational or safety risks. In this dataset, there were 339 recorded failures compared with 9,661 normal operating records. In other words, normal cases were approximately 28.5 times more common than failures. This imbalance in this dataset makes failure easy for a conventional model to overlook. The project goal was therefore not simply to achieve high accuracy, it was to detect as many genuinely high risk machines as possible while keeping false alarms at a practical level. From an operational perspective, the model should help a maintenance team choose among three actions: one, to continue operation; second, to monitor the machine more closely; or third, to arrange an inspection for the machine. Now let us move to the dataset. The project uses the Predictive Maintenance Dataset, which contains 10,000 records and 14 original columns. The features describe several parts of machine operation. Product type identifies low, medium, or high product quality. Thermal variables measure air and process temperature. Mechanical variables capture rotational speed and torque, while tool wear records accumulated operating wear in minutes. The prediction target is the machine failure column, where 0 means no failure and 1 means failure. The dataset contained no missing values and no duplicated rows, which gave us a clean starting point. However, as the next slide shows, clean tables can still contain inconsistent labels. Now let us move to data quality checks. I did not assume that a dataset with no missing values was automatically reliable. I compared the overall machine failure target with the 5 individual failure type indicators. This check identified 9 machines labeled as failures without any recorded failure type. It also found 18 records with a failure type even though the main target was 0, and 24 records containing more than one failure type. The most frequently recorded mechanisms are heat dissipation failure, overstrain failure, and power failure. Importantly, I excluded all failure type columns from the model inputs. These columns describe the outcome and reveal information that would not normally be available before a failure, including including this would cause target leakage and produce unrealistically strong results. Now, let us move to the end-to-end workflow. The project followed 6 connected stages. First, I acquired the dataset directly from the Kaggle. Second, I prepared the data by standardizing names, checking labels, and removing identifiers and leakage variables. Third, I engineered new thermal and mechanical features. Fourth, I compared a dummy baseline balanced logistic a dummy baseline model with the balanced logistic regression models, random forest model, and XGBoost model. Fifth, I explained the selected model using conventional feature importance and shape values. Finally, I packaged the trained model and deployed it through Streamlit so that users could enter operating conditions, obtain a probability, and understand the reason behind the prediction. Now, let us move to feature engineering. The raw sensor measurements are useful, but machine stress often depends on interactions between them. I therefore created 5 features with physical interpretations. Temperature difference measures the gap between process and air temperature. Mechanical power combines torque and rotational speed. Tool stress combines torque with accumulated tool wear. Temperature ratio represents the process temperature relative to ambient conditions, and torque speed ratio captures the amount of torque relative to rotational speed. These features allow the model to recognize combinations such as high load at low speed or high torque on a heavily owned tool. The final input table contained 11 modeling variables, which became 12 processed features after product type was one hot and coded. Now, let us move to why accuracy was misleading. The dummy model produced 96.6% accuracy, which may initially sound excellent. However, it predicted every observation as no failure and detected that none of the 68 failures in the test set. This demonstrates that accuracy paradox in an imbalanced classification because 96.6% of the machines did not fail, a model could ignore every failure and still appear accurate. For that reason, I prioritized failure recall, precision F1 score, ROC-AUC, and especially precision recall AUC. Recall shows how many failures were detected. Precision shows how many alerts were genuine. And AUC evaluates probability ranking while focusing on the rare positive class. Now let us to operating conditions during failure. The exploratory analysis revealed a clear operating profile for failed machines. On average, failure records had 26.59% higher torque and 36.76% greater tool wear. At the same time, their rotational speed was 2.84% lower. The box probes reinforce this pattern. Failure is associated with heavier load, more accumulated wear, and somewhat lower speed. Temperature differences between the two classes were much smaller. This suggests that mechanical stress is more informative than raw temperature by itself. These are associations rather than proof of causation, but they provide useful evidence and helps us evaluate whether the model's later explanations are operationally plausible. Now let us move to failure rate by product type. Failure risk also varied across product types. Type L contained 6,000 records and had the highest observed failure rate at 3.92%. Type M had a failure rate of 2.77%, while Type H had the lowest rate at 2.09%. Product type therefore evaluates useful contextual information, although it is not sufficient on its own. The visual analysis also show that engineered load indicators separate failure and non-failure cases more clearly than raw temperature variables. This supports a modeling approach that combines product context, original measurements, and physically meaningful interactions. Now let us move to correlation with failure. This chart ranks the numerical features by their linear correlation with machine failure. Torque speed ratio had the strongest positive correlation at 0.206, followed by torque at 0.191, tool stress at 0.190, and mechanical power at 0.176. Tool wear also had a positive relationship with the target. The individual correlations are moderate rather than extremely high. That is expected because machine failure rarely depends on one variable in isolation. Correlation only measures a linear relationship, while tree-based models such as random forest and XGBoost can detect non-linear thresholds and interactions. The correlation analysis is therefore exploratory guide rather than a feature selection rule. Now let us move to data splitting and pre-processing. To obtain a reliable evaluation, I used stratified sampling so that every split preserved approximately the same 3.4% failure rate. The main training set contained 8,000 records with 271 failures, and the untouched test set contained 2,000 records with 68 failures. Within the training data, I created a model training subset of 6,400 rows and a validation subset of 1,600 rows for threshold selection. Pre-processing was fitted inside each machine learning pipeline. This ensured that scaling and one-hot encoding learned only from the relevant training data, preventing information leakage. I also used class weights and an XGBoost scale positive weight value of approximately 28.5 to reflect the imbalance between normal and failure cases. Now let us move to model comparison. The model comparison produces an important trade-off. Balanced logistic regression detected 88.2% of failures, but its failure precision was only 18.2%, so it generated many false alarms. Random Forest achieved the highest failure F1 score at 0.87 and an excellent precision of 96.4% with a recall of 79.4%. XGBoost achieved 98.7% accuracy, 80% failure precision, and 82.4% failure recall. It also produced the best ROC-AUC of 0.9795 and the best PR-AUC of 0.8846. I selected XGBoost for deployment because it provides the strongest probability ranking, and slightly better failure recall than random forest. This makes it well suited to a risk scoring application where the operational threshold can be adjusted later. Now let us move to test set confusion metrics. The confusion matrix translates model performance into actual maintenance outcomes. Of 1932 normal cases, the model accurately classified the 1918 and generated 14 false alarms. Of the 68 real failures, it detected 56 and missed 12. This means the model catches most failures while keeping unnecessary alerts relatively low. However, the 12 missed failures still matter. No threshold removes every error, so deployment becomes an operational decision rather than a purely statistical one. If a missed failure is extremely expensive or dangerous, the organization may lower the threshold to detect more failures, accepting additional inspections in return. Now, let us move to threshold selection. I evaluated thresholds from zero point 0.1 to zero point 0.9 using the validation set. Lower thresholds increased recall but also produced more false alarms, while higher thresholds improved precision but missed more failures. A threshold of zero point 0.5 offered a strong balance on validation data. It achieved 86% precision, 79.6% recall, and an F1 score of 82.7%, with 7 false alarms and 11 missed failures only. The precision recall of 0.8846 is particularly encouraging because only 3.39% of 3 observations belong to the positive class. Still, the threshold should not be treated as permanently fixed. A real maintenance team should choose it using the financial and safety cost of missed failures compared with unnecessary inspections. Now let us move to global feature importance. The global feature importance shows that mechanical load dominates the model's overall decision. Torque speed ratio was the leading feature at 19.9%, followed by mechanical power at 15.7%. Rotational speed contributed 12.1%, tool wear 11.4%, and torque 10%. The stroke ranking of the engineered variables is valuable because it shows that feature engineering added meaningful information rather than noise. The model is not simply memorizing a product category, it is responding mainly to machine behavior associated with load, speed, and wear. Feature importance is global. However, so it tells us what matters across the dataset rather than why one particular machine received its score. Now let us move to shape explainability. To explain both global behavior and individual prediction, I used shape values. The global shape summary shows which variables consistently push predictions towards higher or lower failure risk across the test set. It also reveals the direction and spread of each feature's effect, offering more information than a standard important ranking. The local explanation focuses on one machine. Positive sharp contributions increase its predicted failure product probability while negative contributions reduce it. This allows a maintenance user to see not only that the model produced a high risk result, but which operating conditions were responsible. Explainability makes the output easier to audit, discuss, and compare with engineering knowledge. It supports human judgment and does not replace it. Now let us move to high risk machine example. This is the highest risk example identified in the test data. It is a Type M machine with an air temperature of 301.7 Kelvin, a process temperature of 309.8 Kelvin, rotational speed of 1284 revolutions per minute, torque of 68.2 Newton meters, and a tool wear of 111 minutes. The model assigned a failure probability of 99.99%. The combination is consistent with the earlier exploratory findings. Torque is high, rotational speed is relatively low, and the tool has accumulated meaningful wear. The application translates this probability into clear high failure risk warning and recommends inspection before the next production cycle. This is the practical value of the project, and this is converting complex model output into a direct maintenance action. Now, let us move to the application. So this is the application web page. This is the first page. It demonstrates the Streamlit application built around the trained model. This is our first page. So this is about the dataset overview. The opening page establishes context before any prediction is made. It presents the dataset size, data quality checks, class distribution, available variables, and modeling features. Then next, let us move to application, the next page of our web application, and that is interactive analytics. So this is the interactive analytics web page of our uh, application. These analytics sections allows users to explore the relationships discovered during the notebook analysis. It displays failure rates by product type, operating condition box plots, and feature correlations. Users can therefore verify that failures tend to occur under higher torque, greater wear, and lower rotational speed and can compare product categories directly. Now let us move to the next page of our web application, and this is the detailed evidence page. This full page view preserves the detailed analytical evidence rather than reducing it to a few headline numbers. The users can inspect the complete box plots, the summary statistics comparing failure with no failure, and the correlation analysis. Keeping those details available supports reproducibility and makes it easier to challenge or validate the conclusions. Now, let us move to the next page, which is model evaluation page in our web application. This is the model evaluation page of our web application. So this page places comparison metrics, confusion matrices, and threshold diagnostics together to allow users to see why high accuracy is misleading, how our model is performing. So all model performance related and evaluation metrics are presented here. Then we move to application to the auditable threshold results of our application. These extended performance views shows the detailed threshold table used to support the final operating decision. Then next move to application, and this is our our live risk prediction web page. This is the live this is the live yeah live web page. Oh, sorry, not this, the previous one. This one. So here the operators enter the conditions and they receive a score of if the machine is likely faulty, need inspection or not. So so this is the operational center of the application. A user enters product type, air temperature, process temperature, rotational speed, torque, and tool oil. And this and our application displays the failure probability, a visual risk gauge, the calculated features, and a recommended action. Now let us move to the next page in our web application, which is the explainability and this conclusion. So this is the final page in our web application. So here, the final application page brings explainability directly into the user experience. Global feature importance shows the operating factors that matters across all machines, while local sharp contributions explain why the current machine's risk uh, can be increased or decreased. So now I'll give a leaf demo of the entire web application, which is also available in Streamlit and GitHub, and I'll be giving the links at the description in the YouTube. So so I hope you can see this. This is the um, this is the web application. Yeah, so this is the first page. It gives us the dataset overview, the dataset overview, the first page. Then this is the failure analytics page. It gives the entire analytics, failure rate by product type, then operating conditions, and then the machine failure, the correlation, all the analytics that are important, the exploratory part as well. And then this is the main model part, how our model is performing. Then this is our risk prediction web application. As you can see, I can enter the values over here, and then predict failure risk. As you can see, it has a critical risk because of these parameters, and it is shown by this gauge. Model features, actions, recommended actions, actions of scheduling and immediate machine inspection. So like this. Then we have the explainability part. We have the global feature importance, which features are important. So here is the explanation over here, identifying those features. And then we have local prediction explanations as well, based on the parameters we predicted over here. So yeah, so this is all that we have. So uh, this is all that we have for now. If you like the video, please like and subscribe to our channel. I hope you find it useful. Thanks for watching this video.